morning, everyone. So first of all, I would like to say thank you, everyone, for being here today in my defense. So the title of my dissertation is Big Data Optimization for Distributed Resource Management in Smart Grid. And here is the outline of my presentation. First, I will talk about the introduction and the motivation for using big data optimization for distributed resource management in smart grid. Then I will talk about the research work I have done so far. And finally, I will talk about the future work and the conclusion. So first, let's talk about why we need big data for distributed resource management. So here is the basic structure of the power system. So basically, the power will generate from the central power plant and it will deliver to the customer through the transmission and distribution network. But this is not efficient because of the centralized operation nature. So recently, smart grids has been proposed as a promising solution for the future power system. So in the future power system, more and more energy will be generated locally, mostly from renewable energy. So this distributed generation will become a key component in future power system. So by using renewable energy, it brings a lot of economical and environmental benefits, and it also helps to improve the efficiency of the power system because the power will be generated locally is more close to the user, which can reduce the power loss due to the transmission and distribution. But in return, the power system will be more and more complex. And also, by deploying two-way information exchange, smart grids create a huge sort of big data. The data can be from user, from generation, transmission, or distribution network. So as you can see, if we can effectively use the data we have, like the generation, demand, or pricing information, we can have better balanced demand and supply, and also we can create an extra benefit for user through different energy service here. So of course, the big data and the distributed generation will bring a lot of benefits, but because the system will be more and more complex, it will be very challenging for system operator to guarantee for reliability and security of the power system. The traditional management model, like the centralized management model, it cannot be applied anymore. So we need a new computational model and a mathematical model to handle such a big challenging problem. Therefore, in this dissertation, we focus on big data optimization for distributed resource management problem. So by investigating the distributed resource management problem, so the main contribution of this dissertation can be summarized as follows. First, I propose a new resource management model to improve reliability and the security of the power system. And also I propose a new computational model for our algorithm to achieve the optimal solution for the system. And also by applying big data optimization technique to implement our algorithm using Hadoop MapReduce framework, so we facilitate for practical application of our model. So the distributed resource management problem, there are many things to consider, but we focus on this dissertation, the bitrate minimization problem, the optimal scaling for microgrids, and also some other related work. So first, let's talk about the bitrate minimization problem. So due to the environment policy and also the cheap installation cost of the solar panel, so more and more renewable energy will be generated in the future. For example, California target about 33% of energy consumption must be from renewable energy in 2020, and also it will continue increase in the future. So of course, the renewable energy will bring a lot of benefits, but it's also introduce a new threat into the power system. So here is just one of the example. Here is how the net load of the system. So as you can see here, during the middle of the day, when a huge amount of renewable generation available, so users start using renewable energy to supply the load. So the net load of the system significantly decrease here. And then in the late afternoon, when renewable energy resource is not available anymore, users start using the energy from the main grid again. Then it's made the net load of the system increase significantly here. And it's been very difficult for system operator to satisfy this ramping capability. So it predicts that the system operator needs to satisfy about 13,000 megawatts ramping in 3 hours to satisfy demand for user. So this is one of the famous issues in California net load, which is a Dept problem. And one possible solution to handle this issue is we use microgrid to compensate for the net load of the system. So the microgrid will use more the energy from the system, the main grid here, and then it will generate more local energy during the high demand periods here. But because the objective of the microgrid is want to minimize the energy cost, they don't want to have the system operator to reduce the peak rate here. So the possible solution is the system operator will offer the microgrid some reimbursement, so that microgrids will participate in the peak rate minimization problem. And then there are two questions we need to answer here is how much microgrids will receive reimbursement from the system, and what is the optimal resource scaling of the microgrid to minimize the peak rate of the system here. There are two key questions we need to answer here. So we consider a system with one distribution system operator for sort of DSO and N microgrid. And we also consider a set of T energy consumption time slot. So microgrids, in order to satisfy demand, they can buy the power from the main grid, or they can generate power locally. So we can calculate the energy cost of the microgrids at this equation. So this is the amount of power is buy from the main grid, and this is the price of the power, and this is the power is generated locally, and this is the cost to generate power. And then microgrids can solve the cost minimization problem to determine how much is buy from the main grid and how much is generated locally. So the objective function is minimize the energy cost, and we have power balance constant here. So this is the amount of power is buy from the main grid. And this is the total demand. This is the amount of power generated locally. This is the amount of power from energy storage device. And this is the power generated from renewable generation if available. So by solving this optimization problem, so the microgrid can determine how much is buy from the main grid and how much is generated locally here. So here we use the superscript 0 here to denote the optimal solution. But this is the case when microgrids don't participate in the peak rate minimization problem. Then, based on the amount of power requested from the main grid, we can calculate the ramp of the system between two time slots here. And this is the net load of the system as time slot T, and this is the net load of the system at previous time slots. Then we can calculate the peak ramp of the system we need to satisfy. In here, we select the maximum element of the ramping vector. So now we want microgrid to reschedule to compensate for the net load. In our work, we want microgrid to help the system to reduce the peak ramp. But when the microgrid deviate from the original optimal point, it incurs an extra cost, and we can calculate in this equation. So this is a new total cost of microgrid when it deviates from the original optimal point. But in return, microgrid will receive the reimbursement from the system. Then we can calculate its pay up at here is the reimbursement. GN is reimbursement from the system, and this is an extra cost. So we can calculate microgrid pay up by this equation. So in a similar way, we can also calculate the pay up of the DSO. So basically, by reducing the parameter system, so the DSO also saving some cost here. So this is the cost function to satisfy the parameter of the system. Here is the original case when the DSO had to satisfy the parameter of the system. Here, when microgrid participate in the pitch rate minimization problem. So because the system, the DSO had to pay for microgrid some reimbursement, so we can calculate the DSO pay up at the saving cost minus the total reimbursement they had to pay for the microgrid. Then we can calculate the social welfare of the system at the total pay up of the DSO and all microgrids in the system. And because the total reimbursement microgrid receive is equal to the total reimbursement the DSO offer. So as you can see here, the variable reimbursement GN has been removed from the equation. So we don't have variable GN in the social welfare. So we can solve the social welfare maximization problem to achieve the optimal solution for the whole system. But as you can see, we cannot determine the amount of reimbursement because the variable reimbursement has been removed from the equation. So we need to find a new mathematical framework to determine the reimbursement for microgrids. And Nash bargaining is one of the good solutions here. So basically, the Nash bargaining is used to model the bargaining interaction between two players. So in order to achieve the Nash bargaining solution, we need to solve the maximization problem with the objective function in the Nash product. So the U1 and U2 here is the pay up of user 1 and user 2. The D1 and D2 here is the disagreement point of user 1 and user 2. So the reason we select the Nash bargaining solution here is because it allows us to achieve the fair allocation of benefits between microgrids in the system. And also it's guaranteed microgrids achieve the positive pay up because we have the minimum benefit the microgrids want to receive is which is corresponding to the disagreement point. So by applying the Nash bargaining solution framework into our problem, so we can formulate this optimization problem to achieve the Nash bargaining solution. So the objective function here is the Nash product of the DSO and all microgrids in the system. So the first part here is the pay up of the DSO, and here is the pay up of the microgrids. So by solving this optimization problem, so we can achieve the optimal solution here. So we can determine the closed form solution for reimbursement. So it will cover an extra cost when microgrids deviate from the original optimal point. And also it will receive a certain fraction of the social welfare of the system. But the problem here is we can only find the closed form solution for reimbursement. We cannot find the closed form solution for energy resource scaling of microgrids. But we know one property is that the optimal resource scaling of microgrids will maximize the social welfare of the system. So what we need to do now is we need to solve the social welfare optimization problem to determine the optimal resource scaling of the microgrids. So there are two ways to solve this problem. The first way is we need to have a central controller to collect all information from the microgrid. Then we can solve the problem in a centralized fashion. But it will violate the privacy of the microgrid. Therefore, we approach the second way if we design a distributed algorithm so that microgrids individually select the strategy.
Your whole thing is more of optimization.
Yeah.
You just took a power system as an example, basically.
Yeah.
You could have applied to any other problem. For example, 20 years ago, before you were all born, the telephone lines, depending on when you call, in a particular country or particular state, the price was changing.
Yeah.
And also first minute it was $3 to call China or India, and then second minute.
43 cents.
No, like that. Basically, you can apply the same thing to that.
Yeah, in the later part we have.
So you're not a power system per se. This one, you take an example and okay, it meets well because that is the trend now. Everybody talks about smart grid energy. So let me apply it. So you get an additional. Okay, I'm also a smart. Am I correct like that?
Yeah, I have another work about wireless network virtualization.
I think from his point of view, he's more kind of algorithm.
Yeah, that's what I meant.
Yeah, exactly.
So it is just a power system as an example he has taken as an application.
Well, he considers a lot of microgrid specific concepts. So he actually models the microgrid, which has energy storage, distributed generators, dynamic model. So it's not kind of a model that can be applied to anything. He plans over all of the stuff.
Yeah, even those models are not from the electrical point of view, from the cost point of view. He doesn't go into the power system or the impedance and that type of thing. That's what I'm saying.
No, he's not an engineer.
Yeah, that's what I meant.
Engineering
So it is not the power systems. It's just at the high level, like an economic guy. We also do. For example, energy. Many of them in the TV and others, they claim that they are experts in energy, but they are lawyers and like that. That's what I meant. It is not the nuts and bolts of the microgrid or whatever it is. Yeah. I'm just trying to put where your thesis stands.
Yeah, thank you.
I think that's a power system and the data managed in the middle.
Yeah.
So now the second way is we need to design a distributed algorithm to solve our optimization problem. And
I had the same concern yesterday's presentation. He has also the same things and all those things. It was more of a mathematical thing he had than the power systems.
Yeah, his math part impressed me a little bit. Yeah, some part okay, it's very nice. Yeah, but I agree with your part.
So an ADMM is one of the possible framework to apply for designing a distributed algorithm. So the basic idea of ADMM is if we have optimization with two block of variable S and G, then we can solve the optimization problem in a distributed way. Like this. First we write a Lagrange function, then we do the iterative procedure here to achieve the optimal solution. So first we optimize the Lagrange function over the variable S while considering the variable G and lambda as constant. So the next step is we optimize the Lagrange function over variable G. We treat the S and lambda as constant, and finally we update the dual variable. So we repeat this procedure until it's converted to the optimal solution. So before we apply the ADMM, we need to transform our problem into an equivalent one by introduce the new variable here. And then we write a Lagrange function for this variable. So basically this is the Lagrange multiplier for our constant here, and this is a penalty term for this constant, and then we rearrange the Lagrange function. So we have this form, and we are now ready to decompose our problem into a smaller one. So we treat all other variables as a constant, and we group all variables belonging to the DSO into one sub-optimization problem. And then we have a sub-problem for the DSO like this. then we treat all other variables as constant, and we group all variables for microarrays into one subproblem. And then we update the dual variable. So we repeat this procedure until it's converted to the optimal solution. So the whole procedure of our distributed algorithm can be summarized in this equation, in this algorithm. So the basic idea is we decompose the original problem into the subproblem for the DSO and the subproblem for microarrays. So first the DSO will show the subproblem, then it sends some information to microarray. Then microarray, after receive the information from the DSO, it will show the subproblem here individually here. And then it sends some information to the DSO again. And the DSO will show the subproblem again. So it will repeat until it's converted to the optimal solution. But our distributed algorithm here is a synchronous algorithm. So it means that after DSO finish the calculation and it send information to microarray, and microarray will do the calculation. So the microarray can start the new iteration only if receive all information from the microarray. It means that the DSO has to wait for all microarray to finish the calculation before it can start the new iteration. So as you can see here, we have one disadvantage here. If the number of microgrids in the system is very large, so this algorithm might take a very long time to convert to the optimal solution. So in order to overcome this issue, we propose a new asynchronous ADMM algorithm. So basically, if we have optimization problem like this, then we can decompose the original problem into the smaller step here. But the only difference here is like we can perform them in a asynchronous fashion. So by applying this framework into our problem, so we can decompose into the subproblem for DSO like this, and also we have subproblem for microarray. So we perform this iterator algorithm until it's converted to the optimal solution, but in the asynchronous fashion. So the whole procedure can be summarized in this algorithm. So the key idea here is like the DSO after finish calculation and receive any information from microarrays, it will start the next iteration. It doesn't need to wait for all microarrays to start a new iteration. So this framework will have the system convert to the optimal solution faster than the synchronous one. So next we use the simulation result to demonstrate the conversion of our algorithm. So as you can see here, the asynchronous algorithm needs more iteration to convert to the optimal solution, but it's faster because it's performed in a asynchronous fashion. And also we saw that our incentive model can have the bit rate resistance model of the system. Here it's reduced about 50% compared to the original net load. And also one important feature we need to consider here is because microarrays, they only want to participate in the bit rate minimization problem if they have some benefits. Otherwise, they don't want to participate in the bit rate minimization problem. And here we plot the payout of the microarrays. So as we can see here, the microarrays receive the positive payout from the system. So it means that microarrays will participate in the bit rate minimization problem to have some extra benefits. So that's all the work for the bit rate minimization problem. So the next work I want to talk about is the optimal scaling for microarray. So the microarrays has been proposed as the solution to improve the system power quality of the system. So one special feature of microarrays is it can operate in normal operation mode, or it can operate in the Icelandic operation mode. But it's possible that when switched into the Icelandic operation mode, the microgrid might not be able to fully satisfy demand for all users because of the ramping constant of the local generator. So the problem we try to consider here is we want to minimize the operation cost of the microgrid in the normal operation mode. But also when it's switched into the Icelandic operation mode, we also want to minimize the amount of loss that microgrid cannot satisfy. So we consider a system with n microgrids. So in order to satisfy the demand, so each microgrid can use the local generator, or it can buy the power from the main grid, or it can exchange the power with neighbor to satisfy the demand. So when microgrids switch into the Icelandic operation mode due to the security reason, so we have new constant for microgrids because now microgrids cannot get the power from the main grid anymore. So the power here is just from the local generator, or it can be from the neighbor. But is it possible that microgrid cannot fully satisfy the demand for all users? So here is the amount of load that microgrids cannot satisfy. So for all other microgrids, they operate in the normal operation mode. We still have a load balance constant here. It means that microgrids have to fully satisfy demand for all users. And also we have ramping constant when microgrids switch from the normal operation mode into the Icelandic operation mode. Then we can formulate the cost minimization for microgrids, and we also want to minimize the amount of loss that microgrids cannot satisfy for user in Icelandic operation mode here. And we incorporate all constants in the operation, in the normal operation mode and in the Icelandic operation mode. So because we incorporate a lot of security constant into our problem, so it's become a large-scale optimization problem, and it's very challenging to solve this optimization problem in a centralized fashion. So we also use the ADMM to decompose this problem into smaller subproblems, and each smaller subproblem can be solved in different computers. So the whole algorithm for parallel algorithm can be summarized here. So the basic idea here is we decompose the original problem into the normal operation subproblem and the Icelandic operation subproblem. So first we solve the normal subproblem, then we send some information to the different computer, and different computer here will solve the Icelandic subproblem. Then it will send information back to the normal operation problem, and this procedure will be updated until it's converted to the optimal solution. So we use a simulation result to demonstrate the conversion of our algorithm. So our algorithm converts after about 40 iterations. And also we demonstrate the efficiency of our model in reducing the amount of load that microgrids cannot satisfy. Here you can see like only a spot number of microgrids, and also just small amount of microgrids had to reduce the loss when it switched into the Icelandic operation mode.
Islanded operation, right?
Yeah, Iceland. Yeah. So because like we design our algorithm so that it can run on multiple computers to reduce the computational time, so we need to have framework so that different computers can exchange information, and also we need to allocate a different computing job for different computers. And the Hadoop MapReduce framework is one of the good model here. So basically the MapReduce brain model is used to process a large amount of data. So the first step is the input data will be split into smaller parts. Then it will be processed by the math and reduced here in parallel fashion on different computers. Then we write the result into the output file. So as you can see, our parallel algorithm framework, it fits into the math video model. So math will solve the Icelandic subproblem, and reduce will solve the normal operation subproblem. So in order to run math video programming model, we need to write a math function and reduce function here. In the math function, we will solve subproblem for Icelandic operation, and in reduce here, we solve the subproblem for normal operation. And we run our algorithm on the Hadoop cluster we built in our lab. So this is cluster with 8 computer inside. So 1 master computer and 7 slave computer. And we run our algorithm and we compare the running time. So normally when we have large number of microarrays, the computational time is not increased too much, because the master computer will distribute the computational job to different computers. So that's all the work for microarrays optimal scaling. So now I will talk about a little bit some other work about the distributed resource management. So the first work I want to talk about, like the decentralized reactive power compensation. So different from DC network, in AC network, the utility company needs to deliver both reactive power and active power for user. But the user only pay for the active power. They don't need to pay for the reactive power. So you can imagine reactive power and active power like the beer we drink every day. So the real power here is the drinkable here. So because the utility company only charge for active power, so from the viewpoint of utility company, they want to deliver more active power to have higher benefits.
No, this is very common. I have seen this type of pictures in places.
I know.
It's a beer showing the active and reactive power.
Yeah, my point is that, okay, this for reactive power, the power is fine here for your specific area. But in the other area, you seldom see beer in the 50.
Yeah.
We see that after the
No, when the people, even in the classrooms, when the people, difference between the active and reactive power is a very common picture.
Yeah, I
They
know.
use it.
So, and also one important thing is, if utility company deliver too much reactive power, it will increase the power loss and also increase the voltage fluctuation. So in order to improve the efficiency of the power system, so one possible solution here is user will generate reactive power locally, and the rest of the reactive power demand utility company will deliver to the user. But the key problem here is because user, they never pay for reactive power. They don't have motivation to generate reactive power. So the utility company here need to offer some reimbursement for user to generate reactive power. So we consider a system with n user here. So the power will ingest into the system from here, or user can generate reactive power and active power locally here. So we need to determine now how much reactive power and active power user will generate locally to achieve the optimal solution for the system, and also how much reimbursement user should receive from the utility company. So we also use the net bargaining framework to handle our problem. So we formulate the optimization problem to achieve the net bargaining solution. So here is the payout of the utility company. And the next is the pay up of the user. So by solving this optimization problem, we can achieve the optimal reimbursement and also how much active power and reactive power user should generate. So the other work I want to talk about is about the resource allocation for wireless network virtualization. So the virtualization has become a popular concept in many different areas, like in computer science we have virtual machine, we have virtual memory, and now it's applied to wireless network, and we have wireless network virtualization. So here is the basic structure of the wireless network virtualization. In the lowest level, we have a infrastructure provider, so who are the infrastructure and wireless resource. Then the mobile virtual network provider will lead the network resource and create a virtual resource. Then the mobile virtual network operator will operate and assign the resource to service provider who focus on providing service for user. So there one problem we need to consider for wireless network virtualization is because multiple virtual network will operate on the same physical network here. So we need to determine how much resource we allocate for different virtual network here to achieve the minimal operation cost of the system. And also one of the special feature of the wireless network virtualization is because the multiple virtual network operate on the same physical network, so any failure happen on the physical network, it will affect the multiple virtual network at the same time. So we need to find an optimal solution so that even some failure happen on the physical network, the virtual network still survive, it still continue to operate. So we formulate our optimization problem to achieve a minimal operation cost for the system, and also just in case some physical link in the physical network broken, the virtual network still be able to provide a service for user. So here we incorporate all constants for the system. So the normal state means that all physical link in the physical network is work very well. And the link failure stay constant here means that when some physical link is broken, the virtual network still be able to provide service for its user. So because we incorporate all constants into our optimization problem, so this also become a large-scale optimization problem. And we also desire a distributed algorithm to solve this optimization problem. So that's all the work so far I have done here. So now I will talk about the future work. So in the future, like more and more users will install a solar panel, and they will become a prosumer who can consume or produce energy. So the new scenario here happen is if prosumer they have more generation than demand, then they can sell energy to its neighbor to have some extra benefits. But because the power flow now is become two-way, then it's become complicated for the system to guarantee for the reliability. So we need to consider reliability for the system, and also we need to find the framework so that we can motivate prosumer exchange the power with its neighbor. So basically this is a clear problem between the economic efficiency and reliability. So we need to find an acceptable solution for our optimization problem. So this is the work I want to do in the future. And finally, I come to the conclusion. So in this dissertation, I focus on the big data optimization for distributed resource management in smart grid and also in wireless network virtualization. So it has been proved that the microgrid and user have extra benefits, and also the system reliability and the security has been improved.
So if I have to say your main contribution is the algorithm for distributed resource management.
Yeah. So here is a publication. And
Can you go back to? These are all the, yeah. Effectively done, that's all good.
Both of them is both of them is transaction smart grid, and one is communication, one is a parallel and distributed system.
For the transactions of smart grid, can you submit a paper without presenting in the conference, or you need to first submit a?
No, I think it's already discussed. Only
Without conference.
First you need to submit in the conference.
No.
Or directly to submit it, that's what I meant.
yeah, exactly. So
Because in some transactions you need to submit first in a conference. And then you have to submit, you can
but
submit.
in transaction smart grid, even though you submit into the journal, you basically end up with the conference submission. So only for TSD, transaction smart grid. So that's reason you see.
What did you say?
If you submit to transaction smart grid, basically, I mean, either before or after that, you probably don't have the opportunity to submit to a conference.
Yeah. That is true for any transactions.
Yeah.
If you submit your transaction, you cannot submit your conference. But if you submit your conference first, then you can submit your transaction.
Yeah, true.
But that's why. But in some, for example, IEEE transactions and industry applications, you have to present it in the conference first. Even in power electronics and power systems, IEEE transaction power systems, you need to present it in PhD.
Yeah. So that's reason you see you have much more journal paper than conference paper because of TSD.
How much difference they need between the conference version?
Well, TSD is relatively shorter, to be honest. Okay, but the overall, yeah. Otherwise, okay. In the, for example, transaction wireless communication or transaction parallel, something like that, is 40 to 100%. At most, you have 40% for conference. Yeah.
So Shahid was the editor for the transactions small grid.
Yes, started.
No, he's not anymore.
No.
Yeah. Huh?
Right.
Oh, yeah, I know. You told me that. Suppose if a paper is submitted to a conference on in the power systems, can it be submitted to the transaction smart grid also?
At the same time?
Yeah. Because you cannot submit a conference after publishing transactions, but if you are not submitted, in some you can do it.
So
I don't know about smart grid because I don't deal with smart
in
grid.
terms of number of pages, the contribution, the qualities are different in conference.
Yeah. That's why I'm asking whether it can be submitted the same one to the transactions and conference. Because some conferences you need a very high quality. For example, one of our ECCE, there is a very high rejection rate is more than 50% there.
Yeah, we have general meeting, which is a 40%.
Okay.